Okay, girls, in this video I want to talk about intermolecular bonding, and I'm going to try and relate it to electronegativity, right? So if you think about our definition for electronegativity, the electronegativity of an element is the measure of the power of attraction that that element has for a shared pair of electrons in a covalent bond, right? So all the ones on the left-hand side, so the metals, right, they tend to be electropositive because they don't really want to get electrons, they want to lose electrons. Then if you look over on the right hand side of the periodic table, you get the non-metals, okay, and they tend to be electronegative. So the most electronegative element, for example, is fluorine. So fluorine would be a very electronegative element, and something like sodium would be very electropositive, okay? All right, so, and remember, you're talking about S block here and P block here, right? But anyway, say for example, if you take a small molecule like water, if you go and look at the electronegativities for, say, hydrogen, I think I'm just going to pull figures out of my head here, but you can check them with your tables in the book. Hydrogen is probably about 2.2, right? And I think oxygen is about 3.55. So oxygen is a very electronegative element. Hydrogen is like a metal. It's on the left-hand side of the periodic table most of the time. It tends to lose electrons, right? So when you put that into a molecule, and you then what you kind of get to see is that, right, there's a shared pair of electrons here. So the cross electron is from the hydrogen, right? And the dot is from the oxygen. Now these are two oxygen lone pairs that oxygen has anyway, and that's what causes it to be V-shaped. More about that later, okay? But if we just focus on what's happening here, because oxygen is so electronegative, it's able to pull those two bond pairs. So they're called bond pairs. We just call them BPs, right? It's able to pull those two bond pairs up close to itself. And the lone pairs then are creating the shape because they push the bond pairs closer to each other, all right? So you got two lone pairs, right? And two bond pairs. The thing about it is, though, if you were to kind of draw that on a macro scale again, or just zoom out a little bit, what you're really saying there is that, well, the electrons are spending most of the time near oxygen, so oxygen's kind of partially negatively charged, and hydrogen is partially positively charged. So we describe that as polar, because these ends of the molecule are different. It's kind of like the north pole and the south pole of a magnet. This end is negatively charged. This end is positively charged. So that symbol there is a Greek letter. I can't remember what it's called. It's gamma or delta, one of those things. But that's not anything we need to be worried about. Right. But now this is all inside the molecule because those two bonds are intramolecular bonds, right? So that's an intramolecular bond. It's inside the molecule, and it's nearly always a covalent bond, right? Okay, but if you think about it, if there's another water molecule close by, and it's got a negative oxygen end and a positive hydrogen end, then what can happen is that partially positively kind of polarized area of that molecule can be attracted to this negatively polarized end of this molecule, and you get a weaker type of bond, which is called a H bond or a hydrogen bond, okay? But now, that is not in the molecule. It's between two different molecules. So this is an intermolecular bond, right? Very different. So it's between two molecules, okay? So how that came into play in the questions we were doing there recently was, if you take, for example, something like ethanol. So you've got your ethanol here, C2H5, and then you've got your alcohol functional group out here, remember, which is called a hydroxyl group. And that's called hydroxyl carbon there. That guy there is the hydroxyl carbon. So this hydroxyl group is going to have some degree of polarity because, remember, the oxygen is very electronegative and that hydrogen is very electropositive. And anytime you've got a hydrogen bonded directly to a nitrogen, an oxygen, or a fluorine, you get H bonding. So I just call that the NOF group, right? So you get H bonding because these three, nitrogen, oxygen, and fluorine, are highly electronegative. They like to pull electrons towards themselves. Okay? So because hydrogen in this situation is bonded to an oxygen, right? It's one of the NOF elements, nitrogen, oxygen, or fluorine. What will happen then is if a water molecule is close by, the negatively charged end of the water molecule will be attracted to the positively charged end of the hydroxyl group, which is the hydrogen, and that will create a H bond. Okay? Now this H bond means that when you mix ethanol and water, they mix quite well. They're slightly attracted to each other. And the thing that causes mixing is when things are attracted. So it's no problem for ethanol to be mixed with water. However, if you were to increase the size of this part of the molecule, this carbon chain part, so if you were to go up like the question we saw last week, up to heptanol, and there was 7 carbons there, well then only a very small part of the molecule is polar, and any of the water molecules that would be around here, around the heptanol, wouldn't be attracted to this big long chain part. So it reduces the solubility, and in a sense, the higher alcohols aren't really soluble in water at all. Okay, so if you that's the alcohols, right? So the other family we were looking at was, say, the aldehydes. Okay, so what's going to go on here with the aldehydes? Well, if you look at ethanol, okay, you're going to get a different type of H bonding here, because what you're going to get is this attraction. Okay, but if you think about it, if you go back to our NOF, right, the oxygen here is not bonded to a hydrogen, it's bonded to a carbon. It's in this molecule here where the oxygen is bonded to a hydrogen that enables this H bonding type of arrangement here. So you get this little bit of attraction here. So the smaller aldehydes are also soluble in water. But again, that solubility would decrease as this carbon chain gets longer, because the smaller proportion of the molecule is polar as you grow bigger and bigger. Okay? So what does it mean? Well, it means that both of these are soluble in water. But there is a crucial difference. Is if you think about it, if you have any alcohol molecule, right? So this is a different situation out here. Okay? So any alcohol, some ROH, you can get intermolecular bonding due to H bonding from one alcohol molecule to another. So that means that the alcohols can maintain high boiling points because of H bonding. But you don't get that with the aldehydes, right? Because if you think about it, in the aldehydes, really what you've got is an RCH to O group. Okay? So you can't really have H bonding to another molecule because I have to squeeze this in now. Strictly speaking, that hydrogen